bit of about this. So let me start the journey, and just I want to share the fact that I was like you one day. I listened such type of lecture for the first time, and I took this research work later. Fortunately, I took this research work, and now I am in a situation that I am giving you the lecture. You are the future right now. Yeah, you will. Some of you maybe in future will do some research work related to this particular topic. So the topic is nanoparticles are beautiful and widely applicable. So why beautiful? First we shall see, and the application of it we shall learn and we shall see. So myself, as you know, I am Dr. Ratan Das, assistant professor in the Department of Physics, doing some research work in this particular field. Let us, let me give you some ideas related to that particular part. So, as the title indicates that nanoparticles are beautiful, let me first state that what are nanoparticles? These are very small particles. Often you know this particular word, that these are very small particles, and these particles are smaller than even the bacteria and viruses. Here, as you see, that DNA helical rings, it is around 2 nanometer, and protein viruses are around 10 nanometer or 100 nanometer, but the that we deal with the nanomaterials which are less than the size of the bacteria and viruses. So these nanoparticles are very small with which we deal with, and the application of these are very wide applications of these materials have actually. So this particular nanomaterials, actually we just take in the range of 1 to 100 nanometer. Beyond 100 nanometer, we may call it nanomaterials, but application of those nanomaterials are very less. You may have 1000 nanometer particles, but application of those nanomaterials are not that much effective. But if we take the nanomaterials in the range of 1 to 100 nanometer, then it is found that the applications are very high. And again, I want to tell you that the nanomaterials are very small, and they are smaller than bacteria and viruses. Nanoparticles are beautiful. The first slide, the first portion, this is the silver nanoparticles. You can see that there are beautiful colors are there, starting from red, green, blue, etc., etc. These are related to different size of the nanoparticles. Silver nanoparticles. If we have 10 nanometer silver nanoparticles, they may show another color compared to the nanoparticles of 80 nanometer. So various sizes of silver nanoparticles are there, which are showing different color. This is a dark microscopic field image, and the silver nanoparticles of different size and shape showing different color. Here, this is CDSC semiconductor nanoparticles dispersed in water, and they show different color. But if we just vary from 1 to 10 nanometer, they show different color. If you vary from 1 to 10 nanometer size, the nanoparticles of CDSC, you may obtain from green to red. And regarding that particular slide, that particular part, I want to tell you that this is a charge window where the silver nanoparticles or gold nanoparticles are incorporated in glass matrix, and they are used for display in charge windows. I shall come to that part later. Now let me tell about that. The different nanoparticles show different color. Silver nanoparticles show different color depending on their size. The semiconductor nanoparticles show different color varying from the size from 1 to 10 nanometers. Now, nanoparticles are not only beautiful in color, but they are very smart and intelligent too. That's why we use the nanomaterials or nanoparticles. Like sniffer dogs, nanoparticles may smell and detect the presence of toxic element in somewhere, in gas, maybe toxic gas, maybe some toxic element in water or drinking water. That can be detected by using nanomaterials or nanoparticles. And they have wide application in every field, and they can sense the changes in physical parameters, and that's why nanomaterials or nanoparticles provide good information about the presence of toxic chemicals in our environment or any environment we shall want to deal with actually. Now uh, as we have come to know, nanoparticles are beautiful. Varying the size, we can get different color, and nanoparticles are very smart and intelligent too. Now, right now, I want to tell you that about the classification of nanomaterials. So, if we take a cube, and if we any corner of the cube taking as a origin, we have three axes x, y, z, right? If we reduce the x-axis, y-axis, and z-axis to the nanometer range, suppose decreasing the x-axis to the 10 nanometer, y-axis to the 10 nanometer, z-axis to the 10 nanometer, we can have a small 10 nanometer by 10 nanometer or 10 nanometer cubic nanoparticles, right? And that 10 nanometer size cubic nanoparticles are called as zero dimension, because we have reduced the size along the three dimensions. Got my point? If we reduce the size in two axes, I mean suppose y and z-axis, keeping the x-axis along or elongation in a mode, then we can have a one-dimensional nanomaterials. One-dimensional means it is a rod. Okay, two-dimensionally confined, it is a thin sheet, and three-dimensionally confined means we have a spherical nanoparticles, that there may be spikes of nanorods emerging from that spherical nanoparticle, that is called three-dimensionally confined. But zero dimensional means nanoparticles, one dimensional means nanorod, two dimensional is a actual nanosheet or thin sheet, and three dimensional means from a nanopod materials we have a spike like structure. So uh, we can say that there are one dimensional, two dimensional, three dimensional, or zero dimensional nanomaterials. Okay, let me talk about only the zero dimensional one. And related to the zero dimensional, we may have quantum dots. You might have heard about this word quantum dots. Any of you? Have you heard about quantum dots? Yes. Quantum dots are nanoparticles, means zero dimensionally confined along the whole three axes, and this is called nanoparticles. And among these nanoparticles, the semiconductor type nanoparticles are quantum dots. Mind it, what I have told you, semiconductor nanoparticles are called as quantum dots, not metal nanoparticle or any other organic nanoparticles, right? Only semiconductor nanoparticles are called as quantum dots. Now, semiconductor nanoparticles, especially within the range of 1 to 10 nanometer, are called as quantum dots, because in that particular case, in that particular semiconductor nanoparticles, the splitting of the valence band takes place. Just like suppose I do not know whether you have learned about quantum mechanics or not. Probably there is in quantum mechanics you might have learned that there is a potential well. If we just put a quantum mechanical particle inside the potential well, we may have energy level, right? So if we restrict the motion of the particle inside a potential well, we may have splitting of energy levels, right? So if we have a small nanoparticles, then the motion of electron in that nanoparticles are restricted. Mean free path is almost equal to the size of the nanoparticles, right? So the free motion of the electron is get confined, free motion of the electron is actually restricted. That's why the energy band gets splitted in the range of 1 to 10 nanometer. That's why quantum mechanical effect comes into that particular nanoparticles, especially in semiconductor nanoparticles, and energy band gets splitted. We may have discrete energy levels. That's why these particular semiconductor nanoparticles are known as quantum dots, right? Like quantum dots, you may have carbon dots. You might have heard about carbon dots. Carbon dots are very luminescent particles, but they are not quantum dots. They are not semiconductor nanoparticles. Carbon dot is totally different from quantum dot. Quantum dots are nothing but the semiconductor nanoparticles in the range of 1 to 10 nanometer, where the energy band gets splitted. We may have discrete energy level. In the next slide, see this is the cadmium selenide semiconductor nanoparticles in the range of 1 to 10 nanometer. The beautiful color actually displayed by the nanoparticles because of the size confinement, because of the splitting of the energy levels. Now, quantum dots, again I want to tell you about that. They are zero-dimensional nanoparticles and they are semiconductor nanocrystals. What happens that if we take cadmium selenide, the bulk one is like big one, right? This is the scale is there, it is a big particle. And in the nanoparticle, what happens that the valence band gets splitted. Okay, we may have discrete energy band. We may have discrete energy levels. and that's why the beautiful size is, beautiful color is showing by the semiconductor nanoparticles of cadmium selenide. Other semiconductor nanoparticles also show beautiful color, but especially I am taking the example of cadmium selenide nanoparticles. They are showing beautiful color. So if you reduce the, if we increase the size is increasing or reduce the increasing, the band gap actually changes. Band gap changes means valence band, conduction band. There is a band gap. That band gap may change if we decrease the size or just change the size in the nanometer range. That's why in the range from 1 to 10 nanometer, we may have different gap for band gap for different size nanoparticles. We may have different color. Got my point? So uh, here you see there is a band gap. There is a band gap. So if we size increases, band gap decreases, size decreases, band gap increases. In the next slide you may get the idea about this. So from the bulk to the nanometer range, in the nanometer range we are decreasing the size of the nanoparticles. Here band gap actually increases. If the band gap increases, we may have transition. In the different level we may have different color. It is only because of the change in the band gap the nanoparticles, especially semiconductor nanoparticles, shows different color actually. Okay, I have told about the beautiful nature of the nanoparticles, and there's a little bit of physical properties. Now let me go to the fabrication or preparation method. How can we prepare the nanoparticles? There are two approaches. One is top-down approach, another is bottom-up approach. Bottom-up approach means we do construction of the building by brick, right? So we may prepare the nanoparticles by joining atom by atom. This is what is known as bottom-up approach. Means from the very below we do confine the nanoparticles or just structure the nanoparticles atom by atom. But from the bulk one, if we go to the nanoparticles by physical method, what is known as top-down approaches, these top-down approaches are very costly affair. It needs very costly instrument. That's why we the researcher like person don't follow that top-down approach, because these are very costly affair. But there is a significant advantage of top-down approaches. Here we can get uniform sized nanoparticles, right? Just like etching of the material by some instruments, what is called lithographic technique, we may have nanoparticles of different size. Okay, what is known as top-down approaches. But in the bottom-up approaches, we take chemical approach, chemical reaction process, and with that we can prepare the nanoparticles. Okay. Now why the nanoparticles are important? Important because in that particular size range, in the nanometer size range, the surface to volume ratio increases. What is the surface area of the sphere? Surface area of the sphere? You well know you are well known to that. Surface area. I can expect this answer from you. Actually, I am giving you a lecture on a very simplified topic. Surface area. Volume of a cube. Volume of a sphere. Volume of a sphere. 1/4. Surface area of sphere is 4 pi r square. Volume is 4/3 pi r cube. So if we divide S by B, surface to volume ratio, it comes out to be 3 by r. Right? So surface to volume ratio is equal to 3 by r. So what happens that surface to volume ratio is proportional to 1 by r. Surface to volume ratio is inversely proportional to r or proportional to 1 by r. If we reduce the size, means if we decrease the size, decrease the radius, surface to volume ratio increases. Got my point? So in the case of a nanoparticles, the surface to volume ratio is very high. Very high. Similarly, for a cube, the surface to volume ratio is 6 by L. So if you reduce the length, the surface to volume ratio will be high. Okay. So if the surface to volume ratio increases, what happens that in the case of a nanoparticle, almost many of the atoms will be on the surface. most of the atoms will be on the surface of the nanoparticles. If you have a big sphere and if you cut that sphere into smaller uh, small spheres, then you may have huge number of surface area, and with that huge surface area, that may interact with the particular thing that you wanted to, suppose toxic element or any other absorption method or any other particular case, that huge surface area will have the that particular huge surface for the reaction process. Suppose for catalysis, I do not know, there are chemistry students also. If you have the catalysis process, and if there is a huge surface area, then the catalysis reaction will be high. So if you take instead of taking a big sphere, if we cut that sphere into smaller spheres, then catalytic reaction will be high. Okay, so there is an advantage that if we decrease the size of the nanoparticle, surface to volume ratio increases, and for 10 nanometer particles, almost 20% of the atom will be on the surface. If for 3 nanometer particle, you see 50% of the atom will be on the surface. So most of the atoms are on the surface, and that's why they react with the particular things, particular toxic element or particular reaction. They have get the atmosphere to react better. So if we reduce the particle size in a graphical representation, if we reduce the particle size, surface to volume ratio actually increases. Now this high surface to volume ratio actually results in a number of active surface atoms, and which contributes to the improved material properties, because they enhance the reactivity. If more surface atoms are there, reactivity will be more, and high surface to volume ratio in nanoparticle affect the physical properties. Okay, so the more number of atoms something will find, the more reaction will be there, surface reactivity will be there, physical properties will be more, or changes in the physical properties will be more. Now, as just like water, you have heard about surface tension, right? Surface tension is related to surface energy. As most of the atoms are on the surface, or for nanoparticles, surface to volume ratio increases, there will be increase in surface energy, and this is the main reason behind the many good properties that we find in the case of a nanoparticle. It is because of the presence of high surface to volume ratio and because of the presence of high surface energy. Got my point? So in nanoparticle, surface energy is very high, and only because of that it shows all the properties. So we have learned that in the case of a nanoparticle, surface to volume ratio is very high, surface energy is high. Now if we reduce the size, there is a size effect. We can indirectly say that because of the size effect, the band gap changes. Because of the size effect, the term is very important, size effect, in the case of a nanoparticle study. Because of the size effect, we may have different band gap, we may have different surface reactivity. Now, already in the first slide we have come to know that the color changes as a function of size. In the second slide you have got the idea about the silver nanoparticles, that different size shows different color. So if we have different size, we may have different color. Changing the size, we may have color different. So again, I want to emphasize the fact that in the case of a semiconductor nanoparticles, in the range from 1 to 10 nanometer, if we vary the size, we may have different color. But in the case of a gold and silver nanoparticle, if we vary the size from 1 to 100 nanometer, we may have different color. Now, only one two line I want to say about that particular part is that in the case of a bottom-up approach, I mean in the chemical reaction, how does a nanoparticle forms? It is because of the fact that in the chemical reactions, we may have supersaturations, we may have Gibbs free energy. You might have heard about these terms in the solutions. So because of the supersaturations, because of the Gibbs free energy, I don't want to tell about those facts, but only I want to tell you that there may be a formation of cluster, what is known as nucleation, what is known as seed, right? In the solutions, we may have a formation of stable cluster, 13 14 atoms will collapse together, they form a seed, or they form a nucleation in the solutions. Around that nucleation, further atoms will come and they grow into a big nanoparticles. In that process, what happens that nucleation takes place. But before nucleation, in the reaction, suppose in the case of a silver nanoparticles, if we want to prepare the silver nanoparticles, what happens that if we just dissolve silver nitrate in the water, there will be silver ion, there will be nitrate ion, right? The silver ion will be Ag plus. You are getting my idea, I think. Now that Ag plus cannot come together to form a cluster. We have to reduce the Ag plus ion to the Ag0. Okay, and there should be a reducing agent in the solutions. There are different chemical processes are there, but there should be a reducing agent which reduce the silver nanoparticle Ag plus to Ag, silver Ag plus to Ag0, and then this neutral Ag atom will club together, they form a cluster. Around that cluster, that another silver ion, neutral ion will come and they form a nanoparticles. Around that nanoparticles, there will be a stable ligand or a protective layer around that nanoparticles. Okay, what is known as capping agent. So in the preparation of the nanoparticles, we have a reducing agent or have a oxidizing agent, and another is capping agent. These two things are very important, either a reducing agent or oxidizing agent, and then a capping agent. These two things are there. Reducing agent will reduce the metal ion or any ion and they form a nanoparticles. Capping agent will just give a layer of around that particular nanoparticle so that further growth cannot take place. Okay, we restrict the growth actually. Now, so for proper preparation of a nanoparticles, we may have proper choice of chemicals. I mean, reducing agent, capping agent, pH value, temperature, stirring rate, proper atmosphere. These are very important. These are very simple also to control, and anyone using that particular part or controlling that parameters, you can prepare the nanoparticles. Now, after preparation, how can you view the nanoparticles? Because nanoparticles are very small, you cannot even observe by naked eye the bacteria and viruses. Even with the optical microscope, you cannot see the virus clearly. The particles which are less than the size of the viruses, these are very difficult to view by the optical microscope. That's why we need another microscope, sophisticated instrument, what is known as electron microscope. You know, I think that there is a resolving power, there is a resolution of an optical microscope. You heard about that resolution term in the microscope, right? So in the case of a electron microscope, the resolution is very high. Resolution will be very high. That's why we use the electron microscope. In the case of an electron microscope, what happens that if we just throw the electron, highly accelerated electron, then it may have a wavelength. The wavelength of electron is much less than the wavelength of light. Wavelength of red light is 600 nanometer around, but wavelength of electron is around how much? 1.23 around, or 0.53 nanometer. Okay, so the wavelength of electron is very less, as the resolution is related to the wavelength. So electron microscope, the resolution is very high. So if we see the nanoparticles through electron microscope, we may have a beautiful picture like this. I have prepared cubical nanoparticles, hexagonal nanoparticles. These are some 10 images or transmission electron microscopic images of the prepared nanoparticles. Now, this is my picture. I don't want to show you my picture here, but I want to show you this is a scale actually. You can imagine that this is a electron microscope. So how big is the electron microscope? For this only for this particular part, I want to show you my image. This is a scale, you think, and the huge size of the transmission electron microscope, you can get an idea about that. This is a very costly instrument, around 2 crore instrument. With that instrument, we can get the image of nanoparticles. There is only one particular instrument available at Shillong Nehu in the whole Northeast. Only one instrument. We send our sample, we take our sample to that particular Nehu, and we get the images from this particular transmission electron microscope. There is another electron microscope which is available in Tripura University Central Instrumentation Facility, what is known as scanning electron microscope, and with that also we can get idea about the size of the nanoparticles. Now, in the transmission electron microscope, we may have another attachment. What is known as SAED attachment, selected area electron diffraction. In that particular, with that particular instrument, getting the proper part of the nanoparticles, we may have the SAED pattern or selected area electron diffraction pattern in the nanoparticles. With that particular pattern, we can get an idea whether the prepared nanoparticle is crystalline or not. If it is crystalline, we may have different rings like that, and every ring is actually related to the lattice planes or Miller indices, right? So we may get also that particular part in the transmission electron microscope. These are some silver nanoparticles, and that there are some associated SAED pattern of our prepared sample. Now you see, we have prepared triangular silver nanoparticles, and in that particular triangular silver nanoparticles, we have get an HR tab. What is that HR tab? Every atomic position in the nanoparticles, on the surface of the nanoparticles, we may get an idea about that. So how high resolving power a particular TAM instrument has actually, this particular part shows you the atomic position of the atomic position in the picture. Indirect measurement we can get by the X-ray diffraction pattern. This is the X-ray process. X-ray we throw to the sample, it gets reflected, and then diffraction pattern we obtain. This is the sort of diffraction pattern we can have in the case of a nanoparticles, and from the diffraction pattern from a particular single peak, we may get the size of the nanoparticles. So indirectly, from the X-ray diffraction pattern of the prepared nanoparticles, we can get an idea about the size of the nanoparticles. So direct observation is by transmission electron microscope, indirect observation by X-ray diffraction pattern, which gives you the size of the nanoparticles. Not even that, we can get the lattice spacing, we can get lattice constant, we can get stress, strain, energy density, everything from the X-ray diffraction pattern. Those who are smiling, please give give your ear to that particular lecture. Otherwise, half an hour will just pass away. You can get the time to smile afterwards. Now, there are different applications of nanoparticles. Okay, wide applications starting from agriculture to the space, energy sector. Everywhere we have the application of nanoparticles. I want to just quickly go through that part because I want to finish up that. And after finishing this lecture, I shall go to the university. I have a class there. So you see, in around 2032, USD $332 billion business will be there regarding the nanotechnology or nanomaterials. So in every particular sector, we have the application of nanomaterials or nanoparticles. Don't want to mention about that. Different metal nanoparticles have different applications. Different metal oxide nanoparticles have different applications. All these are commercialized already. Now, where the crisis is arising, nanoparticles or nanotechnology come as a rescuer actually. Now, in the next after 50 years, the oil will just end up in the next 50 years, natural gas will just end up. There will be a huge crisis in the next generation will face the heat of that particular crisis. Okay, so the reliever is the nanotechnology, or reliever is the renewable energy sources. How we can get the renewable energy source? The renewable energy source is only there for our case. It is the solar energy. Okay, wind energy is also there. Other sort of oil we can extract from plant also, but this is not still not commercialized. So regarding the renewable energy sources, where solar energy, solar cell, or hydrogen storing or hydrogen fuel, all these are there in the renewable energy sources. Semiconductor nanoparticles, special kind of semiconductor nanoparticles, they can split the water. They can split the water into hydrogen and oxygen, right? We can store that hydrogen and we can use that hydrogen as a fuel. Okay, in near future, after 5-10 years, you will see that car is running by water. Maybe car is running by water, because there may be an instrument, there may be a process where water will be split up inside the car, and the hydrogen gets stored, and the car will be run by that hydrogen actually. But storing, right now the storing of hydrogen is very difficult, and producing hydrogen is very difficult also. In the case of a solar cell, nanomaterials play the role, because if you use the nanomaterials or nanotechnology, the efficiency comes out to be very high. So using the nanomaterials, we can increase the efficiency. What happens for the case of a solar cell is that the cost is very high. With the using the nanotechnology, we can reduce the cost, because business is there, we have to reduce the cost. And the nanotechnology comes as a rescuer, because reducing the cost, it may give you the right proper energy for in future. So regarding that application of nanomaterials or nanotechnology, actually it starts from the laboratory to the industry actually applies those nanomaterials or those established reaction or established process to the market. Now before that, there will be some work in the laboratory, and research output is main important ingredient behind that. So far as the last I mean in 2021 information is concerned, India is not very far away so far as the research output of nanomaterials is concerned. It is in the third part, maybe it is in the second, I do not know, but it will overcome the US and China in near future, I am sure. Okay, for your interest, I want to show you a few slides. Nanotechnology, as you think that it is very new technology, and of course it is a new, because nanotechnology started its journey around 1990. So far as the application is concerned, when the Sachin Tendulkar has started his career, right? So nanotechnology started its journey from 1990, because there were some sophisticated instruments like transmission electron microscope, scanning electron microscope, Raman spectroscopy, micro Raman, X-ray diffraction. All these instruments were available around 1985, and for that reason, it was suitable for the researchers to apply the nanomaterials around 1990. But before that, many scientists used the nanomaterials or nanotechnology, but as they could not able to properly apply those nanomaterials, only because of the absence of sophisticated instruments. Okay, so regarding the history of the nanotechnology, I want to tell you that we know about Faraday. Faraday did many things. Okay, but less known fact is that he was the pioneer in the nanotechnology field. He has prepared the first gold nanoparticles and reported in the Royal Society. Okay, he is the first person who prepared the gold nanoparticles scientifically and reported it in the Royal Society. And this is the display of the Faraday, where he was explaining the gold nanoparticles. His prepared gold nanoparticles were still there in the British Museum till the First World War, and it was I heard that it was later destroyed because of the World War. Okay, and the sample is like this. So he recognized that the color of the gold nanoparticles, this is the color of the gold nanoparticles. Even we prepare it in our lab also, this shows the same color. The color of the gold nanoparticles, because of the smallness of the particles. At that time, Faraday could not able to see the nanoparticles, because transmission electron microscopes were not there, X-ray diffraction instruments were not there. So he could not able to study because of the non-availability of the sophisticated instrument. If at the time of Faraday, sophisticated instruments were there, Faraday could have done many more things in the nanotechnology part. But because of the time effect, he could not able to progress the nanotechnology because of the unavailability of the sophisticated instrument. We are living in a particular era where so many sophisticated instruments are there. We can use that. You are very fortunate that you are using the smartphone. Even in our days, we could not able to see the smartphone, right? In the near future, the advanced smartphone will come, you cannot even think of, right? So not only that, Faraday around 1959 gave a good lecture on the topic. There is a plenty of room at the bottom. This is a famous lecture. Bottom means bottom up approach. If we just join atom by atom, then that process is bottom up approach. That's why he said that in that particular process there is a plenty of room. Plenty of room. There is a huge application. I mean, he want to say that there is a huge application if we just join the atom by atom, or just your if you just challenge that things, then you can have, or you can apply those part in near future. So he envisioned about the future of nanotechnology, saying that there is a plenty of room at the bottom, I mean plenty of application if we just go into the bottom up approach. Okay, if we go back to the history, then you might have heard about the Mayan people. Mayan society, because the film 2012, you might have seen that 2012. It is as per the 2000, as per the Mayan civilization. Around 2012, the world would end up. You might have heard that story. So that Mayan civilization used some nanomaterials in their frescoes, in their paintings. It was found that the material that used for the paintings were nanomaterials. It is because of your knowledge, because of your general GK, I am just sharing those slides. Otherwise, I could not have done that. Okay, Roman used nanotechnology. There is a famous king Lycurgus. Okay, to just value that Lycurgus king, somebody prepared cups, what is known as Lycurgus cup. These are some glass materials where gold and silver nanoparticles were incorporated. And if you just throw light from outside, the cup shows green in color. If you put one light inside that particular cup, it shows reddish in color. So it is a beautiful cup. It is still there. It is known as that Lycurgus cup. Okay, our ancient Ayurveda, they have used Swarnabhasma, right? Swarnabhasma is nothing but gold nanoparticles, the fine gold nanoparticles. Finer the gold nanoparticles, the medicine will be finer, because gold nanoparticles act as a catalyst. Or you might have heard about the drug delivery system. You might have heard about drug delivery system. Actually, gold nanoparticles uh, use, or people use their gold nanoparticles as a drug delivery system, because gold nanoparticles carry the medicine to that particular site of cancer or other part, and the reactivity it actually enhances. Okay, that's why in Ayurveda people use the gold nanoparticles or Swarnabhasma for faster reaction or carry the medicine to that particular site. So in that regard, I want to say you that our ancient people used to know about the nanotechnology. This is a Damascus sword used by Syrian people, Syrian soldiers, and the material actually supplied from India, Kerala part. And the material is actually the carbon nanotubes or graphene sheet. The carbon nanotubes is the hardest materials. So way back 300 BC, way back 300 BC, the Kerala people used to supply the carbon nanotubes materials to the Syrian people to prepare their Damascus swords. If you hold their Damascus swords, if you throw a handkerchief, it will just cut automatically. This much hardest thing is that. So our Indian people used to know about the materials so far as okay. The Have you seen that particular iron pillar? Anyone? Okay, this is the iron pillar near Qutub Minar. Okay, uh, it is built in 375, 1600 years before it was built, but still it is there in that particular situation without rusting. Why? Because there is a lining of nanomaterial, mesa white lining of nanomaterials around that particular pillar. That's why it is still there without rusting. That's why I want to say that Indian people used to know about nanotechnology. Okay, gold nanoparticles later that information of from the information of that gold nanoparticles from Roman, it come to the China, and in different Chinese porcelain people used gold and silver nanoparticles. This is the Chinese porcelain where gold nanoparticles were used. There are some other Chinese porcelain where gold and silver nanoparticles were used of different size. That's why it is showing different color in different parts of the porcelain. Okay, what is important is that one person, chemist Richard Sigmundi, he studied that particular gas matrix. And before the study of the Richard Sigmundi, nobody knows what are the materials actually, why it is showing different color. He used that, he used some technology to show that the glass matrix which contains silver and gold nanoparticles. He studied a lot, and finally for that particular study he was awarded Nobel Prize in 1925. Okay, only because of the study of the fact that the glass matrix that they are in the church window incorporated gold and silver nanoparticles of different size. You see, the earlier nanotechnologists were so bright that they used proper size nanoparticle in proper places so that good display of color can be obtained. Okay, even many good researchers cannot do that. The earlier nanotechnologies, it is that church window were 400 500 years before. So earlier nanotechnologies used properly the silver and gold nanoparticles of different sizes and placed in different places of the glass matrix so that beautiful color can be obtained. Okay, not only that, nanostructures are found in nature also, where in particular butterfly cuticles, butterfly wings, there are some gratings like structure, nano patterns are there, and light interact with that beautiful cuticles, it display different colors. Okay, opal, it is found in Australia, it contains silica nanoparticles of different size, that's why it shows different color. Okay, lizard leg, it contains fine hair like structures. Just at the front of the structures there is a suction like things are there, that's why it can climb the wall. In lotus leaf there are some nanostructures are there, and because of the angle of contact the water cannot wet the lotus leaf. So why I am showing you that different researchers are actually mimicking that things where bioorigins are there. Okay, so following the biomaterials, following that particular structure, people are now preparing some paintings or paints so that water cannot wet or dust cannot just attach to that particular paint, what is known as biomimicking is very important field. Nanotechnologists are used that particular, or somebody are many people of nanotechnologists are interested in that biomimicking actually. Uh, Last but not the least, I want to show you that we as a researcher in the Tripura University, we are doing some research work related to nanotechnology, and we have a small lab like nanophysics and nanotechnology research lab. We are doing some research work on silver and gold nanoparticles, some semiconductor nanoparticles, as well as some magnetic nanoparticles, right? We have applied the nanoparticles for antibacterial activity. Now we are working on cancer also, some plant germination. Why plant germination? Because it is found that silver and gold nanoparticles may act as a faster germinating agent for that process, and even it enhance the growth also. We have sensed the some pesticides in water using silver. We have sensed fluoride, we have sensed dye, and there is some photodegradation of dyes. There are some application of magnetic material as a soft magnetic materials, application of LED, application of solar cells, etc., etc. So the Bendu is there. He also did some research work in the Department of Physics. Here Mitu Mem is there. So she also did some research work in the Department of Physics. Everyone doing some research work, they are publishing in a particular journals where lots of good peoples from America, Europe are publishing. So they are competing with those peoples actually. We are also struggling to compete with that, and we are as a small contribution to the whole research of India so far as nanotechnology research is concerned. We are just little bit contributing around that particular field. So this is the antibacterial activity. I don't want to tell about this. Okay, let me simply tell you that the bacteria are smaller. I mean, nanoparticles are smaller than the bacteria. When we use the nanoparticles through the pores of the bacteria, it may enter or it may attach to the surface of the nanoparticle. It reacts with the enzymes, and that's why it kills the bacteria. So that silver nanoparticle or copper nanoparticle can act as a antibacterial agent. Okay, these are some papers that we have established. Here I want to say you that silver nanoparticle has been found to show some uh, faster germination process and faster growth process of some seed, known seed. Okay, we have found we have used the silver nanoparticles for sensing some pesticides which are there in the water. Actually, farmer use huge amount of pesticides and fertilizers in the field. 80% of the pesticides and fertilizers actually get wasted and it remained in the field. Due to rainwater, it just finally deposited in the water body. I mean, like pond, then lake or river, and finally it gets contaminated. It comes into the drinking water. Okay, because pesticide is very difficult to remove. That's why we use the silver nanoparticles to see whether pesticides is there in the drinking water or not. We have found that we have removed the pesticides from water also. Okay, we have used some nanomaterials or some magnetic nanoparticles as a LED light emitting device. Okay, regarding another thing, the properties of the nanomaterial can be modified using by doping. You might have heard about that. In silicon, we dope with germanium or I mean some phosphorus or like that things. We dope and we change the properties actually. So there is a accelerator there at New Delhi, what is known as the Swift Heavy Ion Radiation Experiment. Okay, if you use that, we can change the material properties of nanomaterials, and using that we can found that the solar efficiency can be enhanced and etc. Uh, the, for solar cell we have applied by using the modifications, and we have found that there is an increase in the efficiency. So with that process we can use the nanomaterials in a better way. Okay, this is you see this is the nuclear reactor in the bark, and there is a chamber here what is known as neutron sources. Using that neutron sources, we can use that neutrons as a signature of magnetic materials, or to study the magnetic properties of the nanomaterials. I have used that particular neutron to study the magnetic behavior of some materials, and we have found that those magnetic material can be used as a soft ferrite for different application purposes. Now regarding this is the end of the slide. What I want to tell you that if you come to the research area, there are huge money is there so far as fellowship is concerned. After PhD also there are huge money is available. You can, if you jump into the research work, there is no shortage of money. With that, thank you very much for your patience hearing. You might have got something from this lecture. At least if you take 20% of this lecture, it is enough. Thank you very much.